today's set of slides, this is session 4. This is on classes, and just to remind everyone, this is not classes in the sense of courses. This is classes in the sense of object-oriented programming. Today and Wednesday are both going to be focused on object-oriented programming. It's a relatively complex topic, so that's why there are 2 sessions devoted to it. So to kick off, what is a class? Why should you care? Well, a class is how you implement a new object in Python. So remember that Python is an object-oriented language, and so what that means is if you have been using Python for functional programming, that is, if you are writing def statements along with the other goodies covered so far, like if, else, for, while, and making use of def statements, that is more or less functional programming, where you're not making any new objects, you're just using the built-in features of building functions rather than objects. So that's where the distinction is. And at the beginning of the course, I went over a few things that I sort of promised relevance on later in this boot camp. And so one of those things is going to come full circle right now. Remember in like one of either, I think it was the second set of slides, we covered what was called the Python model or the Python data model. And this is the notion that in Python, everything is an object, whether you knew it or not. This really goes all the way down to the implementation. The Python interpreter in its source code written in C implements an object called PyObject, which everything in Python is an instance of. So this was kind of the point of that set of slides, which was that integers, floats, everything, they're all their own type of object that Python itself implements. So Python is then extremely object-oriented. I don't know that it could get any more of an object-oriented language. So the general idea here is how can you take advantage of that as a Python programmer? If you are to use Python to its full capabilities, then you should really get into object-oriented programming because it is an object-oriented language. So let's get into, in a very abstract sense, what is an object? And we'll start with a very fun example, which is just a dog. If you're a cat person, I'm sorry, but we're going to run with a dog for today. An object is really anything that has attributes, properties, data, functions, anything that you can think of in your head, which might be a tangible object, could likely be an object in code. So some of the examples that a dog would have in this sense for attributes would be maybe the color of its fur, its breed, name, its gender. The functions it might have are tricks you might teach it, like speak, roll over, shake, chase its tail. It may have interactions with other objects, like play with other dogs, its owner, chasing after cats. And specifically from a coding standpoint, one of the reasons you might be interested in coding up a dog is maybe the data attached to it. Like if you are working for a vet clinic or a chain of vet clinics, there might be a lot of veterinary health record data that gets attached to each individual dog. So this is sort of how all of these principles in the abstract would apply in this example scenario. So let's code up some of these features, and we'll see this in an example. So dogs in Python. The class is how you create the object. The nomenclature here is that a class doesn't refer to one object, it refers to a set of objects. So the root is that this is a a quote class of objects. That's a mnemonic that I attach to it. So the class doesn't refer to a particular dog. It refers to really all dogs here. So when you create an instance of a class, the function that gets called is this function called init. And this is another instance of these two underscores. Remember last week when we were talking about multi-file Python programs, one of the things we talked about was the $init:\.py file. And that was how you would import an entire directory into Python. Whereas here, we're seeing $init:\. As a function. And this is how you create the object, or how it would be constructed given some arguments. The first argument here is always self, and we'll come back to this a little later, but you don't have to give self as an argument. It is simply a piece of the syntax where the first argument is always going to be treated as the instance of the class or the object itself. So self here would refer to a particular dog. And then what the init function does in these subsequent two lines is it assigns a name and a breed attribute, which is passed as parameters to the function. So in action, this would look like I make a dog object and I assign it a variable named Spot. I give him his name is Spot and he is a Dalmatian. Then I have the attributes spot.name and spot.breed, and they are specifically the strings that were passed to the class, to the init function. And then again, a second example here would be Snoopy. Snoopy is the famous beagle from the Peanuts comic, and just like Spot's name and breed, Snoopy has his corresponding name and breed. This in implementation or in practice, this is really all you need to get a class with attributes up and running, is just these few lines. But the caveat is that it's kind of easily broken, because one thing I can do with this construction is give Snoopy a name of 3 and a breed of some list, which I've just filled with the number 037. And obviously Snoopy's name should not be the integer 3, and his breed should not be a list of 3 integers. So that's sort of the downside to this simple implementation, is that it's easily broken. So this may be good for your own personal code, but if you want any sort of error handling, then it complicates somewhat substantially, but not crazily so. This next extension to the code looks a little more complicated, but it's hard to do anything significantly more complicated than only, it's hard to do anything to 4 lines, which is not a significant complication. So I want to take a second here and just really break down what's going on. So there were 4 functions that got added to this class with an init function at the top, and they're all doing one of 2 things. First off, this @ property and @name.setter or @breed.setter, these are examples of what are called decorators. We'll see more of these in a second, but what decorators do is they take a function and they modify its behavior slightly. It is possible to make your own decorators, but that's somewhat outside the scope of this bootcamp. If there is interest in hearing about that, we could make it part of the final set of slides, but it is we're not going to be going into how to make your own decorators, at least not with the current plan. So let's just break down briefly what these decorators do. what the property decorator does is it makes the subsequent name of the function, so in this case that would be name, or down here it would be breed, is it makes that the name of an attribute which you can access without having to call like a function. And we'll see this in an example on the next slide. And what is seen here is that it's returning a value which is not just simply self.name, it's returning a value which is self._name. This is a very conventional way to store an attribute under the hood, which the user does not have access to, which you can then alias to self.name using properties. So if I have, say, Snoopy.name in the previous slide, say this construction would now be calling this function. That's what I mean when I say property functions make it so that you can call these functions, or property decorators, excuse me, make it so the function which they are decorated onto, you don't have to call it like a function. So this Snoopy.name would then call this this function right here. Then these setter functions are the functions that get called when you go to assign the property a value. And the advantage of this application, or this implementation rather, of this class is that now the name and breed attributes are protected by error handling. Specifically, what they do is when I say now Snoopy.name equals 3, it calls the setter function for the name property. And note that these two functions have the exact same name. They're both def name, and they both take self as the first attribute, but the setter function takes the value that you want to set that property to. And all this does is it checks to see if value is a string, and if it is, it records it into the self._name more private under the hood copy of this attribute. And the same thing happens when you set the breed, the value of the dog's breed. It just checks to see if it is a string, and if it is, it copies it. If not, it raises a type error and just says, hey, this must be a string. You gave me something else. And it sticks in as a string the type of the value for a relatively informative error message. So there's a question in the chat that says, so if you do the @property and @name.setter, do you need the self.name at the very beginning as well? Yes, you do. So the reason for that, and the reason these lines haven't changed, is because these two lines at the top are now calling the setter function. So self.name equals name actually does call this function, and self.breed equals breed calls this function here. If you didn't have that, then like if this was just def init and it passed, then the function actually wouldn't have a name or a breed attribute yet. It would just throw an error saying, I don't have this attribute, if you tried to access it. So to show this in action, there's a quick question in the chat though, says, since Python is weakly typed, couldn't anything you pass be interpreted as a string unless it is explicitly typecast? Technically, yes. Provided it is an object that supports typecasting to a string, then you can. The difference here is that there's really no way to know you as the programmer in implementing this class. For one, this is a relatively simple example of what a dog object would look like. But for two, you as the programmer, it's kind of hard to tell if the name is really a valid name. Like if someone wanted to name their dog 3, just the number 3, then there's really nothing saying that they can't do that. So if you get a string, it may not be, it may not be a real name. It may be a string of just some numbers, but this implementation would not catch that, or it would not raise an error if you tried to do so. There's another question that says, the reason for all of this under the hood works because of how indirect or unspecific Python is. And in that sense, yes. He notes that C++ just uses the private and public decorators and would condense a lot of this. That is absolutely the case. Python has an implementation where everything is public, more or less, and underscores are just a means of noting to users that this should be considered private data. So this self._name nomenclature or style is just noting to users that that this particular attribute, users are discouraged from accessing it, whereas this should just be using a dog.name with no underscore to access that property or to assign that property. So Python does not have private or public, a distinction between private and public data or functions as some other languages have. Thank you for asking that. That's a great question. But you note that with that is noted with the underscores and made clear via underscores. This is somewhat the level of privacy then is if you have a second underscore. If this was self.__name, then that would be a private attribute or a private function sort of with emphasis, which says, hey, users should not, one underscore would be like, users should not access this function or this attribute. Two would be, hey, we really mean that users are strongly discouraged from doing so. So that is a note on Python private versus public implementation in classes. So moving forward now, as promised, to see this in action. Now, when I make Snoopy as a dog, if I try to assign his name equals 3, it finds this line here that I wrote, raise type error attribute name must be a string. And same thing here, when I set the breed equal to this list, it finds the type error that I wrote in the setter function. Attribute breed must be a string. I get a list. So this is how you more robustly implement properties and attributes within Python. The simple way to do it would be if this is just as stated, if this is just your code and you don't necessarily need to worry about error handling, or maybe you do want to worry about error handling in your code, then the way to do that is by putting in these property and setter functions. We'll see some examples more where these properties don't just return something stored under the hood, but one thing that is nice about them is that they can calculate things on the fly, and we'll see that an example of that later in these slides. But nonetheless, I do kind of want to emphasize if you decide to make use of object-oriented programming, which I highly encourage you to do, I would put a special focus on getting comfortable writing these property and setter functions for each of your properties. So moving forward, the way you would then give the dog a function is just with a def statement like you would before. The only difference is that now the function is a part of the class, so it is indented one level. So this is at the same level of indentation as the init and those property functions. And just like other classes, they need to take self as the first keyword. So as I've noted here, self is not a special word in Python. Self is not a built-in word. You won't get any errors if you have something other than self taken as the first argument. It is just simply a standard naming convention for the instance of the class. So when I call, say here, Snoopy.speak, self here is specifically the object Snoopy, the dog object that I have made in Python. And what it does then is it just prints some string, says woof, and it puts in for that placeholder string that object.name. So that becomes then Snoopy.name, which is just Snoopy. And here you have the output string then, Snoopy says woof. And these functions, like any others, can have any number of subroutines. You can have subroutines which are called, which may not be part of the class, which are part of the class. It is really up to you as the programmer insofar as what subroutines you may give these functions and where they're located. So you have basically the same level of freedom as you do outside of a class. So as promised, there are a few things that you can do with decorators that aren't just property and setter functions, one of which is making static methods. And static methods are functions, and this is somewhat abstract. It may make more sense when we see this in an example. Static methods are functions which are a part of the class, but are not bound to the object of the class. What that means is that the function belongs to dog in the abstract sense and not a specific dog. These functions, they are implemented as part of the object or the class because it makes sense to do so. And you make them with a new decorator, which is just @static method. So an example of a static method would be checking if a dog is a puppy. So this function I've written here just returns true if the age of the dog is less than 2. So if the dog is less than 2 years old, we say it's a puppy. I know, that may be there may be other definitions of puppy, but this is the one we're running with for this example. So these functions, they don't take self as a keyword argument. That is because they belong to, like I said, the class and the class of objects and not the specific object itself. So whether or not a dog is a puppy belongs to the object of a dog in the abstract sense rather than an individual dog. So this function, like the others, it just has some light error handling in here. It just checks to see if age is an integer and then returns its value, or otherwise it raises a type error and says that this has to be an integer. So the call signature then is rather than making a dog object, you call dog.isPuppy and you give it the age, and for 1 it returns true and for 5 it returns false. So the line that, or the piece of what you type before the dot is the name of the class, not the name of the object. So here, like I said, rather than Snoopy.isPuppy, this would be dog.isPuppy. And this example, turning back to the definition for a second, they're implemented as part of a class because it makes sense to do so. So implementing the check for whether or not a dog is a puppy or not, that very obviously makes sense to do that along with the dog class. When you're implementing the dog object, it makes sense to be a part of that implementation. So that's an example of a static method. There is one more special type of function, which is called a class method. This differs from a static method in that it can access and modify the state of an object, and specifically because it returns an instance of the class or one of the objects. And this is done with the @class method decorator. So an example of a class method would be to make the Snoopy object that I made in the previous examples. So class methods, they don't take self as the first argument. They take the class itself as the first argument, and that is usually written as CLS. They can take subsequent arguments. Static methods and class methods can take as many arguments as they need to. However, the difference between them and other def statements is that static methods don't take self or the class as the first argument. It's just the arguments you need to fulfill the function of that static method. Whereas class methods, it is the class first and then whatever subsequent parameters you need. So what this does, this returns the class an instance of the class, and what this is doing is calling the init function. This is making an instance of the dog object, and it passes as parameters Snoopy as the name and Beagle as the breed. So the way you call this then is I import the dog object. This is in a file named dog.py, and so hence this import statement is from the dog.py file. I import the class dog, and then I say Snoopy equals dog.snoopy, and this finds the class method that I wrote in here, and it makes our Snoopy object, and he has the name and breed attributes that he should have. There's a question in the chat that says, so would class method be something you'd want to implement for, say, a default profile of an object? Yeah, that'd be a great class. That'd be a great class method. Is you could have some object and a class method just called default, which just constructs some parameter space or something within your object, your structure. So I want to stop briefly. There's another question in the chat. Can I explain from dog, import dog again? Yes. So this line, this class I implemented in a file named dog.py. So this is actually in the Git repository. It's under examples, and let me double check quick. Examples, and then classes, and dog.py. So when I was making this example here on the right, I was running with I was in my example/classes directory. Then from dog import dog, it looks for a file. It finds dog.py, which is this first word, the highlighted, the blue version of the word dog. And within that file, it finds the class dog. Otherwise, if I had said import dog, then dog would be the entire file, which contains a class which is also named dog. So then the call signature to make a dog would not be just simply it would go from dog with name and breed, and it would become dog.dog with name and breed. So that difference is now is in the chat right now, and so that is the change that you would see if I had said import dog as opposed to from dog import dog. So let's stop for questions. This was a lot of new material, so please speak up if you're confused about any of this. I can go back to any set of slides and provide more detail. All right. So quick question in the chat then is, could you give another example of an appropriate time to use static method versus class method? Yes, so let's see. One example I can provide from my own code, in my own Python package, there is an object which runs a simulation of chemical enrichment in galaxies. So the name of this object is single zone, and one of the features it has is that it will take one of its own outputs and reconstruct itself. So the output stores copies of all of the parameters of the simulation, and then there's a function which creates an instance of the single zone class. So it makes a new single zone object based on the parameters that are saved in a given output. And what that lets you do is resimulation. That is a class method called fromOutput. So I'll put a few signatures in the chat. The object which runs these simulations is called vice.singleZone, and it takes keyword arguments as the only arguments. And those keyword arguments are used to initialize properties, and in the same manner that we were showing with these name and breed attributes of the dog. So it's basically those attributes which are then saved along with all of the output. And so the output has memory of the parameters that produces the output. Then what you do in order to produce a new single zone object with the same parameters as one that produced the output is vice.singleZone.fromOutput, and it takes in the name, and what that does is then it returns like I said, it returns the instance of the simulation which produced the output. The reason that is a class method and not a static method is because it returns an instance of the class. If you are looking at a function which should return an instance of that class, it should return an object, then that should be a class method. And that goes all the way down to the base implementation. The class method can modify the state of the object, the static method can't. A static method, at present there are no static methods implemented into this object, but let me see if give me a second to think if there is another example of an object which might have class versus static methods. And so if there are any other questions, feel free to put them in the chat, but I will take a few seconds to think of another example. Somewhat similar to a dog object, you could imagine a person object. And another example of class versus static method would be, say, checking if a person is an adult. You could have a static method that takes in just a number to be the person's age and returns true if their age is greater than or equal to 18. So then the call signature would be person.isAdult, and it wouldn't take a person object as its parameter. It would take in a number, and so you would call it with, say, person.isAdult left parentheses, and then you give it some number right parentheses. And then an example of a static method would be like if you had some function with depending on the properties of the person. Let's say it's just their age. You can have a class method which returns a person object with their age attribute set given from their date of birth. So you could have, say, I'll put this in the chat, person.is adult, and you could give it, say, like 16, or person.is adult 20, and it would return false in the first example and true in the second. Another thing you could do is say, like, and I'm not sure exactly how I would do this. Let's say we'll celebrate Clara, and we'll use her date of birth. And so then a separate example would be Clara equals person.from date of birth, and she was born May 18th, 2019. So we would have some construction like that. Whereas the static objects, the function is called with the name of the class, and then dot, and then the name of the function, and the arguments that go after. Let me know if that answers your question or clears up your confusion, Rachel. If
yeah, thanks.
Awesome. Good. So let's take another 10 seconds or so and take some more questions on classes, properties and attributes, and class and static methods. All right. Well, if there aren't any more questions on that, let's go ahead and move forward. I'll do a quick recap though, just since this is a lot of new syntax. It would be good to see this again. So this is back at the beginning of this class, where we just had the few lines that set these attributes. And the problem was that it was easily broken. So we gave these attributes then each a property and setter function in order to handle the errors and enforce some strict type handling under the hood, so that you couldn't break the object and give it properties that are a given type that it shouldn't have. And that solved the problem of allowing a name which was not a string and a breed which was not a string. There may be other, if you write a class for research, there may be other values which are obviously not allowed. Say, for example, in my own code, there are simulation parameters which are not allowed by value. Like there are certain physical parameters which are positive definite. So then you can have error handling, not only checking for a number, but then you can raise an error, say if the number is negative, or if it passes, if it's a fraction, then you know it should be between 0 and 1, and you can raise an error if the value that is passed to the setter function is either negative or greater than 1. So those are some of the deeper checks that you can put in here. Though in principle, determining whether, to address the question, the previous question of checking for a name that may not be an actual name, that in implementation is hard to do. Like I said, here we would have to have some whether checking if the name of a dog was actually a valid name versus some nonsense series of characters, like someone just smashed their hand on the keyboard a few times. That would be a pretty complicated algorithm, which you could write, but is just beyond the scope of this example. oftentimes programmers, that's an instance where if you are sharing code, should be clear about the types of errors that will be raised by your code and what type, not only types, but range of attributes or range of values that the properties can be set to. So then moving forward, then the static method was created with, excuse me, here we go. This is the syntax. It's a def statement like any other. This looks exactly like the def statements that would otherwise happen outside of the class. They just have this @static method decorator at the top. And just like the def statements that happen outside the class, they don't take self as the first keyword argument. And this is why this is exactly why they cannot modify the properties of an object, because since they don't take self as the first argument, then an instance is not passed to them. Remember that noted on this slide, self is not a keyword. It is the instance of the class that is passed to the function. Here, self refers to the Snoopy object itself. The static method does not take self. So that right there should really exemplify that these classes do not have the ability to modify an instance of the class or an object because they are not given one. Instead, they just fulfill some basic function. Class methods are created with this syntax. They take CLS, which is the class itself, as the first argument, and they're preceded by this @class method decorator. Another name for class methods, which might be familiar to those of you coming from other languages and might lend insight because it's a relatively intuitive name, is factory methods. Class methods produce instances of the class. They produce the object of the class, one of the specific objects that the class, that the attributes and functions are valid for. And so in that sense, factory is a relatively intuitive name because it's producing instances of the class, producing objects. So if there are no other questions that have come up in the past few minutes, the latter half of these slides then pivot in scope to syntactic sugar and magic methods that you can give classes. So that's a relatively different topic than what we've been talking about. So if there are no other questions, and I'll pause again in a second for some more questions in the chat, or if people just want to speak up. But otherwise, I would propose we take the 5-minute break just a few minutes early and reconvene in a few minutes. So let's go ahead and hear some questions if you have them. Going once, going twice. All right. Well, if there aren't any new questions, comments, or concerns, let's go ahead and take the 5-minute break. I will click pause on the recording, and we'll take our 5-minute break. All right, we are recording again, so welcome back, everyone. Before moving on to the next half of the set of slides, I'll just make one final anecdote on the previous slides we looked at, specifically that class and static methods in practice are used fairly sparingly. They are really used mostly when you're looking at a given function where it would make sense to associate it with the class. In general, class and static methods can be implemented entirely independently of the class itself, and you might just make some def statement entirely independently of the class, and you can achieve the functionality of that def statement without making it a class or a static method. But if it makes sense to associate it with a particular class or with a particular set of objects, such as, in this case, determining if a dog was a puppy, it makes sense to associate that with the dog object. And creating Snoopy as a particular instance of a dog object, it makes sense to associate that with the dog class. So hence the implementation of a static method and a class method to do so. But the functionality, the key difference between a class method and a static method versus just say when we called Snoopy.speak and the function just printed Snoopy says woof, the difference is that the class and static methods can be implemented entirely independently of the object itself, whereas that speak function required the name of the dog, and so cannot be achieved outside of the class. That's the primary difference between class and static methods versus some other function within the class. So let me go ahead and get back to screen share. So we are now looking at still looking at the dogs in Python slide. Can I get a quick confirmation in the chat that we are seeing this slide? Thank you, Robert. So moving forward then, the next set of slides focus on something called syntactic sugar. And this is how you implement some nice features that will become apparent in the examples in the example that we isolate for this set of slides. But what syntactic sugar does is lets you write code which is interpreted the same. And remember that word interpreted. Python is an interpreted language. So the Python interpreter will treat two lines exactly the same as one another, except one is more readable or prettier, more intuitive, hence the usage sugar. There's one version of a line of code which is sweeter, quote unquote, than the other. This is something that you have been using all along. You just don't really realize it. And to take advantage of syntactic sugar, there are a set of functions which you need to write. And that this particular set of functions is called magic methods, which enable the prettier version of the line. So the most clarity that that all of you will find in syntactic sugar is probably in just some example comparisons. So this is how you would implement item assignments, item access, string casting, or calling an instance of a class or an object as if it were a function. You give it these special these special functions, which are called magic methods. And just to clarify again, this is still two leading and two trailing underscores. Python has there's a number of files and functions in Python which fulfill a very specific purpose, which have some name which is both preceded and succeeded by two underscores. And And the examples here are this item access. If I were to say, take the 0th element of a list, sublist X, the function it calls is x dot underscore underscore get item underscore underscore, and it passes 0 as the argument to this get item function. Same thing with call, except now when you place parentheses here instead of the square brackets, it calls the call function. And this implements basically calling it as if it were a function. So like f of x, f doesn't have to be a function. It can be some object with this call function written within the body of the class. Then if I were to say run item assignment in much the same way as a list or an array would run, on some list or array x, it calls x dot underscore underscore set item underscore underscore, and it gives the index within the square brackets as the first attribute, or sorry, not attribute, parameter, and the value to be assigned as the second. Then when you call string of x, if you typecast to a string, it calls this string function, and this function fulfills a slightly different purpose, which we'll see in a second. But what is really getting called here, both of these functions have something to do with string casting, but this specifically is the one which gets called when you typecast to a string. But I've included them here because they are similar. But this is the one that is called when you typecast. And just to let you know, this is not the only form. In fact, we'll see even more in in several slides. But there are many more magic methods which you can implement in your classes to make use of syntactic sugar. And so here's a link to just a list of just a very long list which I have used as a reference before on what magic methods classes can take. But the bottom line here is that if you want an object that you write to allow item access or item assignment like this, then you would give it a function, a def statement named get item with these two underscores. So you would write def underscore underscore get item underscore underscore, and it would take self and some index as the arguments. We'll see examples of this in a second. So this is our example, which I'm kind of gonna carry through the rest of these slides. And this is a polynomial object. The idea here is that the features we're looking for are, as properties, the coefficients and the order of the polynomial. If I give it some index I want it to return the ith coefficient. So if I index it like a list with, say, the number 2, I want the coefficient in second on the x squared term. And if I call it with some number x, that should evaluate the polynomial with the known coefficients of the polynomial. If I assign it, so if I say f and I give it some index I equals a, that should assign the ith coefficient to the value of a, modifying that coefficient. And we'll also give it some relatively nice string representation. So this is in the Git repository in the example package with this is just, I think I brought this up last week, but this is just an example package with some objects and some functions to show you guys how all of this might get stitched together into a miniature Python package. But this is under polynomial.py under the mathlib subdirectory of that package. So that is a code which is in the Git repository and is there for all of you as an example. But we're going to be going through that code here in these slides. So the first pieces I'm gonna skip the simple implementation and go straight to the property and coefficients implementation. So if you were implementing this class and you were documenting your code along the way, the doc string for the class goes right between, it goes right after the declaration of the name of the class. And usually, it doesn't have to be first, but by convention, the init function goes first. And the doc string would go directly between the declaration and that first function, usually the init function. So remember then, at the bottom here, when I say self.coefficients equals coefficients, this calls the coefficients setter function. So this here, here's the decorator, which denotes that this is the setter function at coef.setter. This, and now the body of this function is fairly complicated, but that's a little by construction. This is a good example of what we would call, or what a software engineer would call, production level code, where there's pretty robust error handling in here. This first checks to see if the value is either a list or a tuple. Then it makes sure that everything in that list or tuple is a number, and then it typecasts it to a NumPy array with this underscore here. And if one of them is not a number, it raises a type error. It says I have a non-numerical value in the coefficients. This next block proceeds very similarly. It says if this is a NumPy array, and remember NumPy.array is not the type identifier for the NumPy array. It's NumPy.ND-array, the n-dimensional array. And then just like before, it checks if everything is a number and then pulls a copy of that NumPy array, otherwise raises some error and just says this is a non-numerical value. And if it is not a list, tuple, or NumPy array, then it raises an error and says that I need one of those and tells you what type it got. So this is performing a simple function, or fulfilling a relatively simple purpose, but is a good example of production level code. And some of you might find some of you might find it useful to put aspects of that in your own classes, because instead, if I just took this assigned value at face value, then I'm leaving myself open to errors that I might make, accidentally giving it something that is not a list, and then that would cause other errors down the line and make things difficult for me in debugging code. So it's somewhat up to you guys in your own personal code. If you put things like this in there, it will make it very obvious to you. If I see this error message, attribute coefs must be either a list, tuple, or NumPy array, got whatever it may be. That is it. That's an error message that you wrote, and it makes it very clear to you what went on and what went wrong. Somewhat just like the attribute or the properties for the dog object, the coefficients property here, it has the same decorator as before, and now it's returning again this value which is stored under the hood, and this is just the copy which is stored. But another example of a property is what was promised a few minutes ago, is a property which actually calculates something on the fly. The order of the polynomial, that doesn't have to be stored as an attribute. Instead, it can calculate something on the fly, and what it's doing here is it's finding the length of that array, subtracting 1, and returning that as the order of the polynomial. The reason being a second order polynomial, a quadratic function, has 3 coefficients. It's ax squared plus bx plus c, so abc. So for 3 coefficients, the order is 2. And for 4 coefficients, the order is 3, and so on and so forth. We'll see this in action kind of at the end. The next piece we need to fulfill our fulfill the to-do list for this object is a get item and then a call function. So the get item function is what happens when you give it an index and you access an element, just like with a list or a tuple. And what it does here is it just says, if I have an integer, return coefficients and index that NumPy array with that value. And as the comment notes here, if I were to care about other errors which might get raised, the NumPy array will raise index errors. If anything, it's out of bounds. So that's somewhat outside the scope here, or not. Rather, it's not necessary to do so. You could, but it wouldn't necessarily. But it wouldn't be necessary to have an index error be raised when this is out of bounds. And that's because the NumPy array will do that for you. And so then calling requires this function. These are all pretty intuitive names to give these functions. They're pretty easy to remember once you start working with them, but it's common to need a reference. So don't feel like you're falling behind or anything if you need to look at a reference for what these magic methods do. They take a little bit of memorization. The call function can take any number of parameters. It just depends on what is relevant to your code. Like all of the others, these do take self as the first argument still. They're not special methods like the class or static methods. They are just normal def statements. They just have a very specific name. And so then if I am calling a polynomial object, this is intended to evaluate it at some value x. So it takes the value x in as the parameter. And what it does is it first starts at 0 and then just adds x raised to that power multiplied by the coefficient. So that starts at 0. So x to the 0 plus the first plus the 0th coefficient, x to the 1 plus the first coefficient, and x to the 2 plus the second coefficient, and so on and so forth, to evaluate the value of the polynomial, and then it returns the result at the end. Are there any questions thus far? I'll stop for a few seconds. We've talked about a little bit of an extension of what we were talking about before, where we have a property calculating something on the fly, and now a couple magic methods. And we haven't seen these magic methods in action yet, because once we cover all of them, we will show that at the end as kind of a big punchline. All right. So I didn't hear any questions. I guess if you did ask a question, you were muted, but so do feel free to speak up and interrupt me at the moment if you were muted. One last anecdote on this is that sometimes documentation will refer to, quote, callable objects. And in general, that will refer to function, def statements, def statements outside of a class specifically. But if a piece of documentation for something you are interested in says that some parameter or property or whatever should be a, quote, callable object, that can also be an instance of a class with a call function. So in this instance, if some function you were interested in needed a callable object with of only one parameter, which accepted just some number x as the parameter, this would be a valid object for that. Self here does not count as one of the parameters of the function, and we'll come back to that in a second when we see this example in action. So just continuing to check items off our list. Another thing that we haven't done yet is item assignment. Item assignment is done with the setItem function, also 2 underscores. Every magic method has these 2 underscores at the beginning and end. And it takes the index to assign and the value to assign in that order. So here we take in the index as an integer. It first checks if the index is between 0 and the order of the polynomial. And then it checks that the value it is being assigned to is also a number. And if all of those checks pass, it assigns then the coefficient at that position within our NumPy array to that value. And if not, if any of these fail, it raises some error with some error message that tells you what went wrong under the hood. That fulfills the item assignment function. The only remaining piece before we see this in action is a string representation. And we don't have to, and I won't piece this code apart in too great of detail because we'll actually see it and what it is actually doing on the next slide. But what's happening is this is just taking each of the coefficients and printing them to some precision, whether they're positive or negative, and then x to some power in that order. And just to note, as I noted before, the str and repr functions fulfill slightly different purposes, and that is also coming on the next slide. This it's noted here. String is called when you typecast, but repr is called when you run a line with just the object in IPython or a notebook. So something like this. This would call the repr function, but if I were to typecast, it would call the string function. So this is then what we just coded up in action. So I have imported. Remember, my package is just the example Python package that I have put together for you guys, and I'm importing the polynomial object from its math library. The init function takes in either a list, tuple, or NumPy array, calls the coefficients.setter function. It finds that it is a list, and it finds that everything in here is a number, so it makes the polynomial object with no errors. Then when I just run example, hit enter in IPython or the same in a Jupyter notebook, it prints this string of 1.0 plus 2 times x to the 1 minus 1x to the 2 plus 3x to the 3 minus 3x to the 4. I can then index it just like a list. The 0th element gives me the first coefficient, which is 1. 1 gives me the coefficient on the x to the 1 power, which is 2. I can call it at the value of 0, and it evaluates the polynomial. Same with 3. I can assign a given item. This is then the 4th coefficient, so the coefficient on x to the 4th. It was previously -3, and I'm now giving it +3. And so then I evaluate it again at the same value of 3, and I see indeed the returned value did change. It has the attribute coefficients, which gives me this NumPy array, and it has the attribute order, which is 4, noting that this is a 4th order polynomial. The highest power on x is x to the 4th. And then the string representation is modified by the fact that I have changed the coefficient here, and that is then reflected on this string representation. So this is essentially re-implementation of the one-dimensional polynomial that NumPy provides. So this is a good example of what kinds of things are happening under the hood when you use an object like NumPy poly1D object, the one-dimensional polynomial. So let's pause for questions, and just to reiterate, it's important to know that these def statements that you're writing in classes, they are very similar to other def statements that you have seen in the past. The primary difference is that they take self as the first keyword argument, and that these magic methods really just have a special name. That's the primary difference here. Item access and item assignment, calling an instance of a class, these are what this is really doing under the hood is just looking for a def statement with a very particular name. And that's really all that you need to do all of this. So again, we'll pause here for questions. Going once, going twice. All right. So going forward, we'll see a few more instances of syntactic sugar, and then and we will see how you will use syntactic sugar to do what is known as emulating numeric types. This is just more syntactic sugar. This is more functions with 2 underscores at the beginning and end of the function name. So if I call x plus y, what Python actually does is it looks for a function which is tied to the object x and is named underscore underscore add underscore underscore, and it passes y as the parameter to that function. The plus equals function is basically radd, and just like plus for subtraction, there's an x.sub for multiplication and x.mul. Divided by does x.div, and just like for addition, there is an rsub and there is an rmul and an rdiv function. Unless you are wanting this construction, unless you are wanting plus equals to do anything other than x equals x plus y, you don't actually need to write this function. It will automatically perform the function of this function, unless you tell it otherwise. So it's rare that you would need to implement this this functionality if you have already done this one. So there's just a few other examples here showing, the modulo operator is x.mod, and equivalence comparison can be done with this EQ and NE function. So again, just like get item, call, and set item, these are just functions with very specific names that if you write them, you will be able to use the plus sign like any other numeric type. And same with the minus, multiplication, division. You just got to write the function with the right name. So to emulate numeric types with a polynomial, I am going to implement addition and subtraction of polynomials, equivalence and equivalence comparison. And in doing so, a couple extra useful versions will be plus x and minus x. And this is just the unary positive or unary minus operators. So there's a question in the chat: would you have to use the underscore functions if you overloaded the operators? So for those who aren't familiar, overloading in is a feature that is in C++, but not the original C language, which allows you to give functions the same name, but accepting different types. So in C++, you could have a function with the same name that takes, say, one integer and then maybe two integers, or maybe an integer and a string. And it knows itself which function you're calling based on the types of arguments that is being passed to the function. The short answer to that is you cannot overload operators in Python. If if you wrote two functions with the name, if you wrote the getItem function twice, let's say, then the first one is actually going to void the second one is actually going to void the first one. You have just redefined it. That's all. That's it. You've redefined or remapped the getItem function if you rewrite it. So overloaded functions will your code will run, but it will not do what you will think it will be doing if you're coming from C or C++. So that is not a feature that you should attempt to move over from the C languages. Great question. Great question. Instead, what I have done in my own code is I have written subroutines to the getItem and setItem functions. Just like any other def statement, they can have subroutines. Like I've written subroutines to getItem that perform it for a string, and then another one that performs it for an integer. Then the getItem function is just as simple as, hey, is this an integer? Send it to that function. Is it a string? Send it to that one, and so on and so forth. So that's how you can implement a getItem or item access with multiple types. So okay, let's return to this example. Do continue to put questions in the chat, or just speak up if you have them. So we'll start with the unary positive and unary negative features of the polynomial. So if I just say plus x and x is a polynomial, then that's the same as the original. So I don't actually have to do anything. I just return the same polynomial. The self here, remember, is the instance of the class. It is the polynomial object for which I am calling this function. So I can just send it right back if I'm doing a unary positive. But a unary negative, you just take the negative of each of the coefficients, and you have the negative version of that polynomial. So what you can do is take the coefficients and just take their negatives. So negative I for I in self.coefficients, that just accesses the attribute, flips the sign on all of them, and then sends that as a list to the init function for a new polynomial. So and I've noted here these magic methods, they can return really anything. There's nothing there's nothing going on under the hood that is preventing these objects from returning anything other than a polynomial object. If you want an object which has magic methods that return something other than instances of the class, or instances other than what is conventional, you can do that. You should just make sure that it makes sense. You don't implement syntactic sugar where it doesn't make sense to do so. If it doesn't make sense for an object to have item assignment, then don't give it a setItem function. Just give it a function whose name is intuitive. So I somewhat gave up the answer to this question, but we can see who was paying attention. Why isn't it required for this host function to actually call polynomial and create a new polynomial object? Why was that allowed? There's the feel free to either speak up or just put it in the chat. Anyone? Anyone want to jump in? Going once, going twice. All right. It's because self will always be an instance of the class. So self is an object. It will always be an instance of the class that you are coding. So that's guaranteed. When you have one of these functions, the self parameter, which must always be first, is just whatever object you're calling the function for. So if I have a polynomial and I call plus x, which is the same as calling x dot underscore underscore pos underscore underscore parentheses, self in that case is the polynomial x, and so you can return it right back to the user. If there are questions on that, or if people are confused, please ask questions. So we can then write the function to let you add polynomials, and this is pretty easy to do. In practice, when you add two polynomials, you just take the coefficients on the same power of x and you add them. Easy enough. So in implementation in the code, then that's just a simple sum of the two coefficients in the same position. So what this does is I have written the add function. It takes in a polynomial object, hence self, and another polynomial object. And if it first checks that that object is a polynomial, because if I write x plus y, I'm not necessarily guaranteed. If I know that x is a polynomial, I'm not necessarily guaranteed that in implementation that y is a polynomial. I could take a polynomial and try to add 3 that maybe, maybe that would return a new polynomial with the first coefficient modified. But in this case, we're just gonna make things a little simpler and just say that these are two polynomial objects that we're adding. So polynomial 1 plus polynomial 2. And all it does is it says, all right, I'm going to have a list of new coefficients. The resultant polynomial is going to have a different set of coefficients than the old one. And its order is going to be the maximum of either x or y, self or other. And plus 1, because remember, a second order polynomial has 3 coefficients. A third order polynomial has 4 coefficients, and so on. And we've initialized each of the coefficients to be 0 at the beginning. And then for each, for I in that range, from 0 to the order of the new polynomial, we say, all right, if this is within 0 and the order of the first polynomial, add the first polynomial's coefficient at that position. And if it is within the range of the second polynomial, do the same from the second polynomial. And then you just return, and then once the for loop is done, you return a polynomial with that set of coefficients. So this is as straightforward as taking 2 lists and adding the components in each position. So the 0th position components get added and the first position components get added, and so on and so forth, until you've reached the end of both lists, and then you make a new polynomial object out of that. Then what you can do is to implement the subtraction method. This example takes advantage of code you've already written to just add the negative So this was the motivation for implementing the unary positive and unary negative functions, is that now the same, and this is the same as, and as this comment notes, this is the same as saying return self plus minus other. And the non-syntactic sugar version is self dot add other dot neg, and that, so this takes the unary negative of the other polynomial and passes it to the add function. So we're implementing subtraction by adding the negative of a given polynomial. The final pieces, before we see this in action, the final pieces of this emulating numeric types business for this polynomial was an equals comparison. So the basic idea is that if two polynomials are of the same order and have the same coefficients, you can say that they are equal. They don't have to be the exact same polynomial objects, but if their coefficients are the same, then those two polynomials are equal, even in the abstract sense. If you have f of x and g of x, and they're really the same function, then they are equal in the mathematical sense. So what we do here is we make sure that the other object we get is a polynomial and that they have the same order. And the reason this calls all on self.coefficients rather and its comparison with other dot coefficients is because these are both numpy arrays, and when you run this operation, you actually get an array of Boolean values. So if all of the coefficients are equal, this block in here will evaluate to a numpy array whose elements are all true. So then the two polynomials are equal if the all function on that array evaluates true. Otherwise, if their orders are not equal, or if the other object is not a polynomial, you can say with certainty that those objects are not equal. They should not be equal to one another. So you can just simply return false. So it's worth noting too that this implementation of the not equals comparison is not actually necessary. This is the default form of the not equals comparison. So def not equals is just returning not self.equals. That's a very straightforward implementation of that. If you have equals comparison, then not equals should just be the exact inverse of whatever was returned from that. So a piece of advice is, if you ever override that behavior, if you have equals comparison and you have overridden the not equals comparison to do anything other than this, you should have a pretty good reason for doing that, because you don't actually need to do that. And all the way up at the very abstract level, not equals should always just be the opposite of what the equals comparison gives you. So now we're seeing these new features in action. I've made here two quadratic functions out of the polynomial object. X is 1 plus 2x plus 3x squared, and y is 1 plus 3x plus 4x squared. And I've just given them the values x and y. So now I can add them, and they become, as they should, 1 and 1 add to make 2, 2 and 3 add to make 5, and 3 and 4 add to make 7. These polynomials are not equal. They have different coefficients. So x equals y returns false, and x not equals y returns true. I can also subtract them, and it behaves the way it should. 1 minus 1 is 0, so there's nothing here. 2 minus 3 is minus 1, and 3 minus 4 is also minus 1, and so this becomes minus x squared. You can then also call what comes back out of our addition and subtraction operators are also polynomial objects. So you can call those too. So I can evaluate x plus y at the value of 3, and it gives me 80. I can evaluate the value of x minus y at the value of 1, and it returns -2. So this is how these magic methods, which we've written and which are implemented in this polynomial class, are how you can implement, or how you can make use of numeric types, item assignment, item access, calling a given object, adding, subtracting, multiplying, things like this, are all done with these magic methods. So you just write def statements with very specific names. And it's worth noting too that features like this, like the plus and minus, addition, subtraction, are also included in NumPy's Poly1D object. So this is just more of what goes on under the hood when you use an object like that. NumPy's Poly1D object has functions like this. It has, it has a get item. It has a call function. It has these add sub functions, which allow you to add and subtract them. So we haven't done anything new here, but this is intended as an example for everyone to see what really goes on under the hood. And so that concludes this set of slides. And I want to end by calling back to earlier in this bootcamp, specifically to last week's session on when we talked about lists versus arrays and why they are different. So after this set of slides, if it wasn't already very clear to all of you what we mean when we say that lists and arrays are different objects, it should now be quite clear. Lists and arrays are different classes with different source code. They have different set item functions. They have different get item functions. These magic methods, which implement these features, are different between lists and arrays. Some of the features and behaviors are the same, but for the most part, they're different. And that is why you can multiply a NumPy array with another NumPy array. It's because it has a function named __mul__, which supports operations with another NumPy array. The list has no such function. So when you try list1 times list2, it looks for a function named __mul__, which is a function associated with a list object, and it doesn't find one because the class list doesn't have that, but the class NumPy array does. So this set of slides, specifically those in the latter half on syntactic sugar, should lend a lot of clarity to those of you who didn't necessarily have a good handle on why lists and arrays are different from one another. This is why, because these functions, these very special functions called magic methods, are different between the two of them.